All right, now that we got some foundational knowledge about ionic compounds as a whole, we kind of also need to sort of look a little more closely at some other types. Now, the first one we learned about was binary ionic compounds. We're going to branch out a little bit and actually learn about this new one called Polyatomic Ionic Nomenclature. First of all, let's go and define polyatomic ions. These are ions that are composed of, well, again, based on the name, poly meaning multiple, and atoms referring to atoms, composed of multiple atoms with one overall charge. Now, we're going to compare this, of course, to what we learned before, where instead of having multiple atoms, there's a single atom, and the comparison here is monatomic, right? So we're now, again, branching out into something called polyatomic ions, where it's not single atoms anymore, but instead of clumps of them. Now, how exactly the charges work out is not important. The idea, though, is that you do have, again, this grouping. And this kind of shown here in this next section, where we use nitrate as a very common example of a polyatomic ion. So you might recognize this. This is actually a actually super common polyatomic ion that's used in a lot of different things. But basically, notice how it's a single ion, right? We're talking about this as a grouping. Now, this single ion, though, instead of being one atom, is now a group of 4 atoms, where you have 1 nitrogen and 3 oxygens, like you see over here in the Lewis structure. But if you remember, one thing we always do when we draw Lewis structures that have charges, that we kind of do this big old bracket with a minus sign on the outside, which represents the overall charge. So we're not really worried about, say it might be the oxygen or the nitrogen or this oxygen or that oxygen necessarily having the charge. We're actually saying just the whole thing, based on the way it's arranged, has a negative charge. So the formula we write would be NO3 with a -1 charge, and of course that -1 refers to this entire grouping somehow having this -1 charge. Again, the comparison here, right, we're talking about nitrate as a polyatomic ion, but if you include this as a comparison, we've learned this before, which is a nitride ion, right, the ending of IDE, tells us a lot. So it's not just, again, just a systematic way of changing monatomic atoms to ions, but really the point is making sure we compare between nitride versus what we saw here, it's 8. While the nitra prefix tells us nitrogen's involved, the ending tells us a lot more. So again, when we talk about this here, like we said, this is once again monatomic, not polyatomic. By the way, it also has a charge of -3. Just want to point that out there. Typically, many polyatomic ions, anyway, they have an ate or an ite ending, which indicates that the element oxygen is somehow involved. Right? That means oxygen's in there somewhere. Where typically, when it says ite versus ate, just means that ite means it has less oxygen, ate has more oxygen. Now, that again is right there is a good place to kind of check in on some stuff here. So you might be wondering, okay, right, so these are some polyatomic ions. Well, this next bit right here, it's actually going to be a list of common polyatomic ions that are going to be super useful. Let's go and switch over to that. If you look here, this is a list of common polyatomic ions. This is definitely worth keeping around. It's probably maybe the second most important reference sheet that you'll use all year, where, if you notice, you have a giant list of them. Now, it looks intimidating at first, but I gotta be honest with you, really, it's only the left side of this sheet that really has anything. Also, it's kind of broken down in a couple of different ways. First of all, you have a -1 here, you have a -2 here, and a -3 here, which helps you organize exactly what charges are there. And finally, don't forget there's this one up here, +1, which indicates that this is a polyatomic ion that happens to have a +1 charge. So this again helps us recognize it. Secondly, also notice large majority of them again are -1s. There's only maybe half as many -2s and a very, very small amount of -3 charges that are available. So again, as you generally can tell, this is a looks like anyway, a pretty daunting list. But again, there's some patterns here that we can recognize. First of all, let's focus on this group right here. All right, so when you look at this, right, what kind of pattern do you see here is that if you look at the formula, it's ClO4 with a -1 charge, ClO3 with a -1 charge, ClO2, and then ClO, each of those again with a -1 charge. So basically it goes down from 4 down to 0, down to 1. And then also kind of highlighting even more, right, let's go ahead and take a look at this pairing in the middle. You see chlorate versus chlorite. Now, like we said, when we see the prefix chlor, you can kind of assume that it's going to involve chlorine, but then the suffix here of ate versus ite, really what distinguishes the two is that really one is going to have one more oxygen than the other. In this case, 3 oxygens versus 2. That's a great way to start. Chlorate, chlorite. ClO3 minus, ClO2 minus. Now, let's go ahead and go up. So perchlorate is the next one up here. Or perchlorate, right, that's going to have a formula of ClO4, add one more oxygen. How does that relate? Well, again, you kind of see that there's a chlorate here still, but then you have an additional per in front. That per is actually kind of weirdly cut off to where it used to be probably a hyper, right? Hyperchlorate. Hyper, of course, is a prefix meaning above. And so for somehow, some way, they drop the high, and so all you're left with is just per. But again, that's basically saying hyperchlorate, which makes sense because if chlorate, right, is ClO3, then hyper or perchlorate is ClO4 with a -1 charge. On the other end, let's go down here. So from chlorate down to chlorite, ITE means less oxygen than 8. So ite, again, meaning ClO2 compared to ClO3 with a -1 charge. Let's talk about the other side. So going down from chlorite down to hypochlorite. Well, again, what do you notice here? They've added this hypo prefix, which, you know, as a prefix in general means under, it's beneath. Hypo, again, is underneath. And so basically we're saying what is the underneath of the regular chlorite, which would go from ClO2 now to just ClO. That's one way you can kind of use a pattern here, and that shows up every once in a while. A couple other things you want to note. There is this first one right here, acetate, ACETATE, acetate. This one has two different forms, either one are perfectly acceptable. But also that there's a handful here that aren't exactly following the pattern. For example, cyanide. Cyanide, unfortunately, this is a polyatomic ion, even though the IDE ending would suggest it's monatomic. Same thing with hydroxide. This is a stranger one where you have an "ide" ending, but that is not a monatomic substance. Definitely a polyatomic one. Also, a couple things worth noting here. I'm going to use red for just a moment. If you switch over here to look at nitrate, nitrite, compare these two. I'm going to scooch down here a little bit, and I'm going to compare sulfate and sulfite, and then scooch down even more and compare phosphate and phosphite. All right. So the reason why we bring these up is because there's a very common mistake where you assume that 8 as an ending assumes that 3 is the number of oxygens that corresponds to it. So nitrogen, right? Nitrogen with an 8 would actually again mean NO3 minus. However, that's not consistent where again 3 means 8, because if you look down here at sulfate, right? Sulfur is the element involved. That's the root element. You have an 8 polyatomic ion, SO4. And the -2 charge, right? So again, this one does not necessarily mean that 8 means 3. So just kind of keep track of those. It's really not that different from just memorizing some of these patterns. Just make sure you don't associate 8 and ite specifically with 3 and 2. Finally, as a little note here, don't forget our friend ammonium. This one again has an IUM ending. Ammonium, again, not very obvious that it's a polyatomic ion, but is often forgotten anyway because it's kind of over here in this little corner by itself. So don't forget about ammonium. Now, this is your list of polyatomic ions. This is the only list that you'll really have to know. So if you scooch back over here, notice again back on the handout, you kind of have to memorize these. Right? So that's going to be required to be successful. Now, part of that, of course, makes it seem like an overwhelming amount of information, but also, ultimately, this is what helps fluency. This is that foundation that we're talking about. If you understand those basics, understanding polyatomic ions becomes so much more easy. All right, so now that we covered some of the basics of just the ions, let's go ahead and talk about these compounds. So we're going to talk about the nomenclature involving polyatomic ionic compounds. This is when we're going to abbreviate PAI, so polyatomic ionic. Now, when it comes to polyatomic ionic nomenclature, there's some very basic fundamentals that continue here. So going from a name to a formula, right? We're going to see here again as an ionic compound, these polyatomic ionic compounds, so these PAIs, are going to have an overall charge of 0. And that's how it's always been. We're always going to have a neutral overall compound charge. So the positives that are there, the negatives that are there, they have to match up. They have to cancel each other off. But the only thing here that really changes is that when you have multiples of a polyatomic ion, you're actually going to require some parentheses and some subscripts. All right, and typically that'll be on the outside of your parentheses. So again, multiples, right? The key word here is multiples of a polyatomic ion. So this next bullet point, right, or sub-bullet point, if a compound does not require multiples, meaning there's only a single polyatomic ion needed to write a compound formula, then no parentheses nor subscripts should be included. And finally here, charges are not included in the formula, but it's understood to be present, right? So just like any other ions, when we write them out as a compound, the ions aren't actually written out, even though we know they're sort of hidden there. Okay, let's talk through these. Magnesium chlorate. This is the name you're given. Magnesium chlorate. First of all, as always, we want to identify the type of compound. Well, looking at this, we have magnesium, right? That's going to be a metal. Chlorate, which again is going to take some practice, but that ends up being a polyatomic ion. So metal, polyatomic ion, a bunch of nonmetals, right? So that's going to be a polyatomic ionic compound. Furthermore, we know that magnesium, based on some practice and some experience, magnesium ends up being a monovalent metal, right? So we know what the charge of magnesium is going to be. Now, again, going through that process, I'm going to go ahead and label some stuff here. So magnesium, I know, is going to always be a +2 charge, right? So I'm going to scooch over back to a periodic table. So magnesium is always going to be a +2. And then, looking at our polyatomic ions of chlorate, we just saw that one earlier, that's going to be a -1 charge. So I'm going to go ahead and jot a -1 underneath it. So what's the least common multiple between the two of these so that I have the right number? Well, I'm going to need to have a -2 overall to match up with this +2 over here. So that means I had to double the chlorate, but magnesium, I'm good, just 1. So I'm going to have to then translate this work into a formula. So let's see what that formula looks like. Let's go ahead and write out magnesium, which is Mg, chlorate, which has a formula of ClO3. Now again, notice how I'm leaving off the charges for both magnesium and chlorate because they're not involved in the actual written part of the compound formula. Now, let's go and write this out. So I know I have to have one single magnesium, so I don't need to write a subscript there for that. And then chlorate is ClO3, but again, I need to double it. So guess what? I'm going to do a little business like that, and we're good. Magnesium chlorate. All right, let's try the next one. So one more time, going through the process, cobalt to nitrite. Okay, let's figure this out. First of all, cobalt, that's a metal. Also, you have a Roman numeral here, so you probably can anticipate it's going to be a positive cation. So I can write to the side that note is going to involve a multivalent metal. Furthermore, nitrite, this again takes some experience, but that ends up being a polyatomic ion that's recognized, which is down here. Nitrite has a formula NO2 minus. Right? The ITE ending usually is a pretty good giveaway. So again, in terms of going through the process, I know it's going to be polyatomic ionic. Let's see how this plays out. All right, so first of all, cobalt 2. Now, again, I know this is multivalent, so I don't even need to look for it on the periodic table because it already tells me right there, +2, so I'm going to jot down a +2 here. Nitrite, once again, that's a -1. All right, so doing the least common multiple thing here, cobalt to +2, -2, right, to make sure that they match up. So this nitrite's going to be multiplied by 2, the cobalt's going to be multiplied by 1, and so your formula is going to be written to where you have a CO, your nitrite is NO2, and then because I don't need to do anything but double the nitrite to make this a legitimate compound, all right, CO, NO2, and then 2. Notice how we're not doing anything funky like N2O4, right? We're not distributing the 2. And then furthermore, even worse, we're not doing like an NO2 and then just kind of throwing a 2 on the outside somehow, right? That doesn't actually indicate anything except for 22 oxygens, which is far from reality. So let's not do that. Let's do the next one, sodium acetate. Sodium acetate, let's try to break this one down once more. This is going to be a metal. Acetate is one of those polyatomic ions. So I know it's going to be PAI. Sodium I know is a monovalent metal, right? Because it's always going to be +1. So again, going through the process, this is going to be a +1 ion, acetate. Let's switch over to the list of polyatomic ions. Acetate's up here at the top. Got this big old formula with a -1 charge, so let's write it out to where we know it's going to be -1. Least common multiple between these two is -1, -1, or +1, -1, so I only need 1 acetate and only need 1 sodium. So let's see what that looks like as the final answer. We're going to have sodium, Na, acetate, C2H3O2. And notice again, I only need 1 of each, so I can leave it as is. One very common mistake here is that sometimes we'll try to add a little parentheses because we've seen parentheses before around these. And so we're like, oh, yeah, we'll just slap parentheses on there. But unfortunately, if you were to include parentheses here, that'd be considered incorrect. So please, none of that. None of that. All right. Let's correct that. There we go. Try the last one out here on your own. Number 4, rhodium 2-phosphate. All right. Now, going from the formula to the name, though, this one actually ends up being pretty similar. So if you notice here, we're talking about ionic compounds. Only the names of the ions are included. So something we don't include, there's no change in the ending or suffix, really, right? Because when we're talking about these polyatomic ions, they're already ions. They're not really anything that we have to convert. So as an ionic name, we just leave it as is. And then we don't use any Latin prefixes again. So no monoditride, none of that business. All right, here we go. K2CO3. Let's go through the process. So K, that's a metal, potassium. CO3, right? If you're looking at this too literally, or too sort of with too much of a tunnel vision, you might just see a C and then you see 3 O's. Not really sure what to do with that, but again, CO3 clumped together, you would be like, oh wait, actually that's a polyatomic ion. Which one is it? Let's find out. Well, it turns out CO3, let's goosh down here, ends up being carbonate, CO3, right, carbonate, and that's got a -2 charge. So let's try this out. First of all, it is going to be therefore a polyatomic ionic compound because you have a metal and a polyatomic ion. We also know that potassium is a monovalent metal, so we're just going to do potassium, PAI, the monovalent metal. And let's do a little bit of work. Let's try to figure out what's there. Potassium, individual charges, that's always going to be a +1, it's a group 1 element. Carbonate's always a -2. So how do we, again, kind of put this together? Well, actually, again, at this point, really, we can go ahead and write the name. There's no need to really do that math because it's kind of already done for us in the formula. It's really the name that we have to worry about. So in this case, we go and write it out, potassium, right? Because we don't change the name of the ion for metals. But then you see right here, CO3, that's actually just carbonate. Okay, and that's all. There's no need to actually change anything. There's no need to change an ending. There's no need to add the fact that there's 2 potassiums, because again, that's not important at this point for ionic compounds. So there you go. What about the next one here? CaClO2. All right, so let's try this one out. Ca, that's a metal. That's going to be one of those monovalent metals. And then we also have ClO, and then you have a 2 out here. So be careful, right? The 2 is on the outside, so we're doubling whatever is in here. ClO, right? Not CiO, by the way. ClO, this is one of those polyatomic ions. Again, takes a little bit of practice to recognize it, but that would actually be this guy, ClO-. It has the name of hypochlorite. So to kind of get this rolling, it's going to be calcium. Oops, excuse me. Got to write the type. It's polyatomic ionic. This is again another monovalent metal, so there's no need to worry about charges or worry about parentheses or anything like that. It's just whatever you see is what you jot down. So in this case, calcium, and then, oopsies, chlor is not correct. It's got to be hypochlorite. And that's it. All right, so we don't have to worry about this 2 here because as ionic compounds, if I went the other direction, going from this name back to here, you'd have to then figure out all the charges and stuff, right? That's the work you'd have to do otherwise. But for now, all we're doing, again, is taking it from the name, from the formula to the name, and that's basically how it works. Go ahead and try number 7 and number 8. There's a little bit additional work to do there, but I think you'll be able to figure it out. All right. Now, if you have time, go ahead and try out the mixed practice here. You have 16 examples. Notice how they're mixed practice. I don't really tell you exactly if it's going to be a polyatomic ion involved or if it's monovalent ions that make your regular binary covalent ones. And as always, make sure you take the time, identify the type of compound, jot down some notes that'll help you accurately name these, and then that'll do it.